In the previous class, we have seen impulse and step responses of first order system. Today, let us see the step response of second order underdamped system. Second order system will be represented by second order differential equation. D square y by dt square, where y of y is the output. X is the input. If we take Laplace transform, assuming zero initial conditions, then we will get y of s upon x of s. So how you will get 1 upon omega n square s square assuming zero initial condition, y of s plus 2 zeta omega n s y of s. Again, zero initial condition, y of s equal to k x of s. If you find y of s upon x of s equal to k upon omega n square s square plus 2 zeta omega n s plus 1. If you multiply the numerator denominator by omega n square, you will get k omega n square upon s square plus 2 zeta omega n plus omega n square, where omega n is natural frequency of the system, where omega n is the natural frequency of the system, This form is called natural frequency form. Natural frequency form. This form is called time constant form. The constant term must be 1. Where tau square equal to 1 upon omega n square. The coefficient of s square is tau square. The time constant square. The time constant equal to tau equal to 1 by omega n. That is the relation between natural frequency and the time constant. This form is called natural frequency form for second order system. We'll use this form to find the step response of the system. Step response means what is input here is x of s, output is y of s. Here we are assuming that x of s equal to step input, that is 1 upon s, or x of t equal to u of t, that is step input. What is step input? Step input will be like this. Magnitude is unit step input. This is the step input to this system. For that, what is the response? Y of t we have to find. The second order system, if you see RLC circuit, already we have seen that RC circuit is first order system. RC circuit. If you take an RLC circuit, R, L, and C, then it is second order system. If you write the KCL, Kirchhoff's voltage law, what is that? V I of t equal to R I of t plus L di by dt, 1 upon C, integral of 0 to t, I of t, not tau, I of t dt. Okay, tau is correct because limit is 0 to t. Tau is correct. Dummy variable is tau. If we didn't put this t here, then we can put t there. Okay. This is Kirchhoff's voltage law. By using Kirchhoff's voltage law, we got this. This is integral differential equation. If you differentiate once, d v I of t upon dt equal to r di by dt plus L d square I upon dt square plus I of t upon c. So it is a second order differential equation. So it is a second order system. Second order system. Similarly, a mass, a single mass, any mass is there, automatically it becomes second order system. As number of masses increases, the order will increase. So d square x of t by dt square, d x by dt x of t. So second derivative is there, therefore it is a second order system. Second order system. These are all examples for second order system. But here we won't consider the system. Simply we'll take a second order system and we will find the step response. That we will see now. Example for second order systems are this mass spring dashboard system or RLC circuit. RLC circuit. These are the examples for second order system. Now let us find the unit step response of second order system, whose transfer function is represented in natural frequency form omega n square k equal to 1 s square plus 2 zeta omega n s plus omega n square and k equal to 1. If you consider, you will get y of s upon x of s equal to the second order in natural frequency form. Here, let us assume that x of s is a step input, unit step input, that is 1 upon s. Therefore, this becomes omega n square upon s multiplied by s square plus 2 zeta omega n s plus omega n square. Here we are assuming that zeta is less than 1. There are three possibilities for the roots. Maybe the complex roots, maybe the roots may be real, complex, repeated roots, or imaginary roots. There are four possibilities. Here we are considering only one possibility, that is based on zeta. That also we'll see. Then before doing that, if you do this partial fraction, what you will get is S1 and S2 are roots. What are the roots for second order system? S1, one root, another root is S2, that is equal to minus B. Here B equal to 2 zeta omega n plus or minus square root of B square. This is B. 4 zeta square omega n square minus 4 AC. A equal to 1. 4A equal to 1. C is omega n square upon 2A. Here A equal to 1. Therefore, 2. That's all. 2 getting cancelled. 2 getting cancelled. 2 getting cancelled. Therefore, this can be written as minus zeta omega n plus or minus omega n square can be taken outside. Omega n square root of zeta square minus 1. What is the assumption we made? Zeta is less than 1. Therefore, this quantity is negative always. Zeta is less than 1. That's why this quantity is negative always. If zeta is less than 1, the root is complex. The root will be complex conjugate. Zeta is assumed as less than 1. If zeta equal to 1, what will happen? This second part becomes 0. That's why roots will be real and repeated roots. If zeta equal to 1, repeated roots. Repeated roots will get. If zeta is greater than 1, if zeta is greater than 1, always this is positive. That's why roots are real, always real only. Real but not repeated variable. Two real roots you will get. If zeta equal to 0, what you will get? Zeta equal to 0 means first part becomes 0. First part becomes 0. Second part is 0 means you will get always you will get negative value. -1 is I. Therefore, you will get plus or minus j omega n you will get. Only imaginary part. Zeta equal to 0. So how the responses will be for zeta equal to 1, zeta greater than 1, zeta equal to 0, that we will see later. Similarly, for zeta less than 1 also, you will get a different response. Now we are going to see only zeta less than 1. The other three we'll see later, we'll see. Now we will consider zeta less than 1. That's why less than 1 means always this is negative. That's why if you take -1 outside, what you will get? Zeta omega n plus or minus j. If you take -1 outside, it becomes j omega n square root of 1 minus zeta square, because I am taking -1 outside. 1 minus zeta square. If you take multiply both -1, because you are taking -1 outside, so -1 becomes j. So it is a complex root always. Complex root always. This is the root. S1 and S2 are equal to this. For this, we have to find the response. For this, we have to find the response. So here, what are the roots? Roots are, already we found that S1 and S2 equal to, we factorized the second part. We factorized the second part. That's why we can write S plus S1 multiplied by S minus S plus S2. That's what in the previous slide. S plus S1 and S plus S2. Because this minus sign can be absorbed. So we can put like this. Now we have to do the partial fraction. So that's why we are writing A upon S, Bs plus C. Why Bs plus C? It is a second order polynomial, a second degree polynomial. That's why we have to write Bs plus C, that you know. So S square plus 2 zeta omega n S plus omega n square. So if we have to find B and C, we have to find. So what we can do is, we have to find B and C. For that, what we can do is A multiplied by A upon S plus this statement, Bs plus C upon S square plus 2 zeta omega n S plus omega n square equal to omega n square upon S multiplied by S square plus 2 zeta omega n S plus omega n square. If you do the cross multiplication, you will get this equation. If you do the cross multiplication, for this S getting cancelled, A multiplied by S square plus 2 zeta omega n S plus omega n square, plus here S will be there. That's why S multiplied by Bs plus C equal to omega n square. Compare the coefficient of S square. Coefficient of S squares are compared, then A plus B equal to 0. A plus B equal to 0. You got one equation. If you compare coefficient of S, here the coefficient of S is 2 zeta omega n S. Here the coefficient of S is C. That's why 2 zeta omega n S, 2 zeta omega n A plus C equal to 0. We got two equations. Now we have to find A. A can be easily found. A from here we can find A. A equal to what? A equal to S multiplied by omega n square upon S multiplied by S square plus 2 zeta omega n S plus omega n square, where S equal to 0. This is getting cancelled. If you put S equal to 0, A equal to 1. A equal to omega n square upon omega n square equal to 1. So A equal to 1 we got. Now we have to find A equal to 1 means B equal to minus 1, because A plus B equal to 0. C equal to A equal to 1, therefore C equal to minus 2 zeta omega n. A equal to 1, therefore C equal to minus 2 zeta omega n. Substitute all these values here. 1 upon S, because A equal to 1, B also equal to 1, therefore S plus C equal to 2 zeta omega n minus 2 zeta omega n. Therefore, here you will get a minus sign. Sorry. Here you will get the minus sign. S plus 2 zeta omega n upon. Now we are why I explained this, because if zeta is less than 1, what happens to the roots? That's why I explained this. To find the response, no need to find the roots. No need to find the roots. Why I found the roots here? Because there are 4 possibilities. If zeta is less than 1, the roots are complex. If zeta, what is the assumption we made? Zeta is less than 1. Therefore, the roots are complex. Roots are complex. That's why BS plus C. That's why BS plus C. And if zeta equal to 1, repeated roots. If zeta is greater than 1, real. If zeta equal to 0, it is an imaginary root. To explain that, I find the roots here. To find the response, no need to find the roots. Here, we are separating this into 2 parts. One is 2 zeta omega n S. So we can write this as zeta plus, S plus zeta omega n whole square. That is equal to what? S square plus 2 zeta omega n S plus zeta square omega n square. So the first 2 terms are here. First 2 terms here. The first 2 terms are here. What is the terms missing? Zeta square omega n square is missing. That's why we have to add and subtract this term, so that we can write S plus zeta omega n whole square plus here what is the term? Zeta square omega n square. That has to be subtracted. So add 1 term and subtract 1 term, minus zeta square omega n square. Up to this becomes S plus zeta omega n whole square. These 3 terms becomes S plus zeta omega n whole square. And what is the remaining? Remaining terms are omega n square minus zeta square omega n square. If you take omega n square outside, what you will get? 1 minus zeta square. 1 minus zeta square you will get. So now omega n square 1 minus zeta square can be assumed as omega d. That can be assumed as omega d. Therefore, the equation becomes S plus 2 zeta omega n upon S plus zeta omega n whole square plus omega d square. Why we wrote this step is, while finding Laplace inverse, it will be easy. That's why we are writing like that. Sometimes in mathematics, we will write deliberately some steps. Here also, we are deliberately writing this step to make Laplace inverse simple. Laplace inverse simple. That's all. So now we can separate this into 2 terms. Instead of single term, I want to separate this into 2 terms. Again, it is also to make Laplace inverse simple. So 2 zeta omega n, S plus 2 zeta omega n. If you take this zeta omega n, you will get 1 more term like this. 1 more term like this. That's all. Up to this, just manipulation. Just manipulation. Now, we have to manipulate this to make it convenient while taking Laplace inverse. You see that what is, instead of omega n, it must be omega d. then only we can write it as a cos term. So omega d is not there. That's why we'll take this step. Omega d equal to what? Omega d equal to omega n square root of 1 minus zeta square. Therefore, this omega n can be replaced by omega d upon square root of 1 minus zeta square. You substitute here, you will get this term. Zeta also taken outside, zeta divided by square root of 1 minus zeta square, omega d upon s plus zeta omega n whole square plus omega d square. Now omega d assumed as a means a upon s square plus a square term is there. That's all. Instead of, if in a function, instead of s, if s plus a is there, s plus b, let us assume that s plus b. Here I am writing that Laplace inverse of, instead of s I am having s plus b upon s plus b square, s plus b square plus a square. If it is there, then Laplace inverse is equal to e power minus bt, that is c of t equal to, the response equal to c of t equal to, or y of t equal to 1 minus 1 by s becomes 1 minus, instead of s we are having s plus b, that's why e power minus zeta omega t, omega nt. Here it must be omega nt, omega nt cos omega dt minus zeta upon 1 minus zeta square e power minus omega nt sin omega dt. That's all. The formula is written here. Laplace inverse of s plus a. What I wrote there is, but instead of a, b is there. Instead of b, is okay. Now we know that we'll take a triangle. We'll take a triangle. Here the angle is phi. Here this is square root of 1 minus zeta square. The length of this side is square root of 1 minus zeta square. Square of it, this side is zeta. So what is hypotenuse? Sum of squares of these two. If you add these two, you will get 1 minus zeta square plus zeta square. That is equal to 1. Therefore, hypotenuse is 1. Therefore, sin phi can be written as square root of 1 minus zeta square upon 1. Similarly, cos phi equal to adjacent side upon hypotenuse zeta. Therefore, tan phi equal to opposite side upon adjacent side. So we can replace this by now we cannot replace. Now we have to simplify. One more step we have to write. C of t equal to we can take this e power minus zeta omega nt outside. Therefore, we can write 1 minus e power minus zeta omega nt, and I want to take that 1 by square root of 1 minus zeta square also outside. That's why I'm getting 1 minus zeta square also outside. That's why that is missing here. That's why it should be multiplied by square root of 1 minus zeta square cos omega dt minus is taken outside. That's why plus. So here zeta only there. Therefore, e power minus zeta omega nt is taken outside. This is also taken outside. Only zeta is there. Therefore, we can write sin omega dt. Sin omega dt we can write. So now we can write 1 minus e power minus zeta omega nt upon 1 minus zeta square. This is equal to what? This is equal to what? Sin phi. So we can write, instead of this, we can write sin phi. Sin phi. We can write as such cos omega dt plus, instead of zeta, we can write cos phi. Cos phi sin omega dt. That's all. So it is equal to sin a plus b. Sine A plus B. That's why this can be replaced by sine A plus B. Sine A plus B. Therefore, 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine A plus B omega dt plus phi. That's all. Where phi equal to tan phi equal to what? Square root of 1 minus zeta square by zeta. Therefore, phi equal to tan inverse of square root of 1 minus zeta square upon zeta. This is the response. What is the response? This is the response. This is the response we derived. 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus phi. Sine omega dt plus phi. You should memorize this. Often it will be useful. Often it will be useful. That's why you have to memorize this. This is the response for second order underdamped system. Second order underdamped system. What is the response? The response, if you see, if you put t equal to 0, t equal to 0, here also t equal to 0, sine phi you will get, t, if you put t equal to 0, this becomes 1, t equal to 0, this becomes 1, sine omega, this also sine phi equal to square root of 1 minus zeta square, these two getting cancelled, the entire term becomes 1. When t equal to 0, this entire term becomes 1. So 1 minus 1, 0. So the response will start at t 0. Response will start at 0. So response will start at 0. Where it will end, we have to substitute in t equal to infinity. If you put t equal to infinity, e power minus infinity equal to 0, the entire term becomes 0. Therefore, it is equal to 1. So it will settle at 1. We do not know whether it will go like this or go like this or it go like this. We do not know. We do not. To find that, we have to substitute various values for t and we have to find. So for that, if you substitute various values for that, we will get the response will be looking like this. Follow my pen. It will follow like this. If you substitute various values, it will follow like this. So this response is when zeta is less than 1. Less than 1. After some time it will settle. It will oscillate. After some time it will be like this. So after this it is steady state response. Steady state response. Before that, what is the transient response? Before that, it is called transient response. The transient part depends upon zeta. Transient part depends upon zeta. If zeta is greater than 1, the response will be like this. The derivation will be different. Derivation will be different because roots are different. Roots are different. If zeta equal to 1, repeated roots, smartest, zeta equal to 1. Zeta is less than 1, it starts oscillating. Overshoot is coming. Overshoot means it goes above the final value. If it goes above the final value, then it is called overshoot. This part is called overshoot. This part is called overshoot. This part is called overshoot. The blue line. Overshoot. If zeta is less than 1, it has overshoot. Zeta is less than 1, it has overshoot. If zeta is 0, it always oscillates. If zeta is 0, the response will be like this. Constant amplitude. If amplitude decreases, finally it will settle. Amplitude is not decreasing. The constant amplitude up to infinity, it is oscillating. It is oscillating. So this is zeta equal to 0. This response is zeta equal to 0. Zeta is less than 1, it oscillates and settles. Zeta is equal to 1, smartest response. If zeta is greater than 1, sluggish response. Sorry, zeta is greater than 1, sluggish response. Sluggish response. This is the example zeta equal to 2, it is plotted for zeta equal to 2. After some time, you'll see all these simulations you can see in MATLAB. I will explain. I will demonstrate some programs. You can try at your home. After this unit, we will simulate all this in MATLAB. And this is a MATLAB simulation. This is MATLAB simulation. Just you have to substitute value of zeta and you have to run. That's all. It will give the response. It will give the response. You can check. That we'll see later. In one class, we will see the simulations. MATLAB simulations. If zeta equal to 0, we'll get sustained oscillation. This is called sustained oscillation. Oscillation is remains there, sustained. This is called sustained oscillation. Sustained oscillation. Sustained oscillation. Zeta less than 1, damped oscillation. That is called damped oscillation. Zeta equal to 1, smartest, that is called critically damped. That is called critically damped. If zeta equal to 1, that is called critically damped oscillation. If zeta is greater than 1, over damped oscillation. Over damped or sluggish response. So we can by using damping we can say over damped, critically damped, under damped, sustained oscillation, undamped. So we can, by using damp, we can say the 4 responses: over damped, critically damped, under damped, undamped. No damping. Damping means amplitude decreasing. No damping. That's why undamped frequency, undamped response. So we can say that over damped, under damped, critically damped, and undamped. 4 responses we have seen. Now we'll see this when zeta equal to 0, undamped response. Undamped response. Zeta equal to 1, critically damped. Critically damped response. If zeta less than 1, under damped response. It means it oscillates and settles. Zeta greater than 1, over damped response. So there are 4 types of response. It depends upon zeta. All the 4 we have seen. Undamped means continuous oscillation without any decrease in amplitude. Zeta equal to 1 means critically damped. Smartest response. Under damped means it has oscillation and settles. Over damped means that is greater than 1 means it takes long time to settle. Long time to settle. That's all. Now we can specify the response. That is called time domain specifications. Time domain specifications. Already I told you that the response, if it goes beyond the final value, then it is called overshoot. Overshoot. This part is called overshoot. This part is called overshoot. The amplitude of this overshoot is called peak overshoot. Peak overshoot. MP. That is called peak overshoot. Peak overshoot. Time taken to reach the first time final value. Time taken to reach first time final value. Here it reaches first time final value is called TR raise time. TR raise time. It is the time taken required to reach the final value. This is the final value. Finally, it settled here. This is the final value. It settled here. And finally, it settled here. So, the time taken to reach first time final value. First time, but it is not remains there. But it oscillates. But the time taken to reach first time final value is called TR. This is the TR value. This is TR. Time taken to reach the final value. First time. MP already I told you. Peak overshoot. The amplitude of amplitude, maximum amplitude. It exceeds the final value. Then time taken to reach this maximum value is called TP, peak time. This is called what? Peak time. At this time, it will reach the maximum value. Always TP is greater than TR. Because after reaching TR only it can reach TP. Therefore, TP is greater than TR. TP is peak time at which the maximum value will occur. The maximum amplitude will occur at TP. Maximum overshoot is MP. Maximum overshoot is MP. Maximum overshoot is MP. Settling time. Another definition is settling time. Another time domain specification is settling time. Where it settles final value. That is called settling time. We can tell some tolerance because it never settles at practical system, never settles at 1. It will oscillate around 1. It will oscillate around 1. This oscillation is called noise. Noise. Noise always will be there. Noise always will be there. Why? Noise always will be there. Noise always will be there. How noise is generated in electronic system? We see that what is Ohm's law? Ohm's law? At constant temperature. At constant, very good. At constant temperature, I is proportional to V. Or Ri equal to V, where R is constant if temperature is constant. Otherwise, R will vary. R will vary as T varies. Therefore, what is the room temperature now? Say 26, maybe 26, around 26. Can I say 26? I can't say because we are breathing. Our temperature is 37. So the temperature is oscillates around 26. We are saying that 26. If we measure, the measuring device will oscillate like this, about 26. That is called noise. Why? Because the measuring device has some resistance. The resistance is in room temperature. Room temperature oscillates around 26. That's why the output voltage will never indicate 26 degree. It will oscillate like this. So all electronic device will have noise. How noise is generated? Because of temperature. Temperature is not 26. It oscillates around 26. It vibrates like this. I may say like that. It vibrates about 26. Because of that vibration, the voltage also vibrates. The output voltage also vibrates. Wherever you have electronic system, noise is inevitable. Noise is inevitable because natural. Because natural. The temperature never be constant. Never be constant. That's why it is inevitable. That's why this output never be at 1 because electronics is involved here. That's why it never be at 1. If it is pure mechanical system, we can keep at 1. Even mechanical system also will vibrate. There are many reasons. We are not going to see all those things. But anyhow, it vibrates about its final value. That is noise. That noise, because of that noise, we are taking some tolerance. Tolerance means, say I am taking 2% tolerance. If it oscillates with about 2% within, that is between 98% and 102%, I am saying that it is settled. I am saying that it is settled. So after this point, the tolerance is 0.2%. That is 2%. The tolerance is, it varies from 98 to 2%. That's why after this, we can say that it is steady state response. Before that, we can say that it is transient response. Transient response. Before this, it is transient response. After this, it is steady state response. We are ignoring that 2% variation. We are ignoring that 2% variation. Therefore, settling time is, this is TS, settling time. After this point, it is within that 2%. It oscillates, but within that 2%. Therefore, this point is called settling time. Settling time, TS. Time taken to reach this point is called settling time. Time taken to reach this point is called settling time. You understand this point? So, raise time is time taken to reach first time final value. Peak time is the time at which the maximum overshoot happens, maximum magnitude happens. Maximum overshoot means the amplitude of this maximum overshoot, that is MP. Settling time is time taken to reach the final value with a tolerance of 2% and remains within the 2%. Then that is settling time. TK ratio is, its amplitude is decreasing. Its amplitude is, the overshoot is decreasing. At what rate it decreases? It decreases. Suppose here the amplitude is B, overshoot is B. Here the overshoot is A, means B by A is called TK ratio. It decreases at this rate, we can say. It decreases at the rate of B by A. And the second overshoot is B, first overshoot is A. So it decreases at this rate. We can say B by A. The ratio between second overshoot and first overshoot is called TK ratio. TK ratio. In the afternoon, we'll see the derivations for all these time domain specifications.